The universe, in its grand and often perplexing design, continually challenges our classical intuitions. For centuries, our understanding of reality was governed by principles of cause and effect, locality, and deterministic predictability. Isaac Newton's laws of motion and gravity provided a robust framework for describing the macroscopic world, and even Albert Einstein's revolutionary theories of relativity, while overturning concepts of absolute space and time, still adhered to a fundamental principle: information cannot travel faster than the speed of light. However, as the 20th century progressed, physicists delved deeper into the subatomic realm, unearthing a set of phenomena so bizarre and counterintuitive that they forced a radical reevaluation of reality itself. At the heart of this quantum revolution lies the concept of quantum entanglement, a mysterious connection between particles that Einstein famously dismissed as spooky action at a distance. Yet, it is precisely this spooky action that promises to underpin some of the most transformative technologies of the 21st century, from unbreakable cryptography to vastly powerful computers, and even the tantalizing prospect of quantum teleportation. To truly appreciate the profound implications of quantum entanglement, we must first understand the fundamental principles of quantum mechanics that give rise to it. Unlike the classical world where objects have definite properties, a ball is either here or there, spinning clockwise or counterclockwise. Particles in the quantum realm exist in a state of superposition. This means a quantum particle, such as an electron, can simultaneously exist in multiple states or locations until it is measured. Imagine a coin spinning in the air. It's neither definitively heads nor tails until it lands. Similarly, a quantum particle's spin might be both up and down at the same time, or its position both here and there, until an observation forces it to collapse into a single, definite state. This probabilistic nature is a cornerstone of quantum theory, distinguishing it sharply from classical physics. Quantum entanglement emerges when two or more quantum particles become intrinsically linked, regardless of the physical distance separating them. When these particles interact in a specific way, their individual quantum states cease to be independent. Instead, they become part of a single, shared quantum state. The properties of one entangled particle are inextricably correlated with the properties of its entangled partner, even if they are light years apart. The key here is not just correlation, like two people drawing matching cards from a deck, but an immediate and inexplicable connection that defies classical understanding. If you measure a property of one entangled particle, such as its spin, the corresponding property of its entangled partner is instantly determined, no matter the vast intervening space. This happens without any discernible signal or interaction passing between them. Consider a simplified analogy. Imagine two coins that are magically linked. When you flip the first coin, it lands on heads. Instantly, without anyone touching the second coin, you know that if someone were to look at it, they would find it has landed on tails. The coins are always opposite. In the quantum world, it's even stranger. Before you look at the first coin, neither coin has a definite state. They are both in a superposition of heads and tails. It's only upon the act of measurement on the first coin that its state becomes definite, and simultaneously, the state of the second coin also becomes definite and correlated. This instantaneous collapse across vast distances is what so troubled Einstein, leading him to coin the term spooky action at a distance. He believed that such an instantaneous connection would imply information transfer faster than light, violating his theory of special relativity. However, experiments over the decades have consistently confirmed the reality of entanglement, demonstrating that while the correlation is instantaneous, it cannot be used to transmit information faster than light. The reason for this limitation, known as the no communication theorem, is that while the measurement outcome on one particle instantly affects the other, the specific outcome itself is fundamentally random. You cannot predetermine the result of your measurement to encode a message. You only know the outcome of the other particle after you perform your measurement and then compare notes classically. The creation of entangled particles often involves specific quantum processes. For photons, for instance, entanglement can be generated through a process called spontaneous parametric down conversion, SPDC. In SPDC, a high-energy photon, often from a laser, passes through a special nonlinear crystal. Inside this crystal, the photon can spontaneously split into two lower-energy photons, known as signal and idler photons. Crucially, these two new photons become entangled. Their properties, such as polarization, momentum, or spin, will be intrinsically linked. If one photon's polarization is measured to be vertical, its entangled partner's polarization will instantly be known to be horizontal, or vice versa, depending on how they were entangled. This method provides a reliable way to produce entangled pairs, which are essential for many quantum experiments and nascent technologies. The existence of entanglement was a point of contention for many years. Erwin Schrödinger, another pioneer of quantum mechanics, also grappled with its implications, famously describing it as the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. It was John Bell in 1964 who formulated Bell's theorem, a mathematical framework that allowed for experimental tests to distinguish between classical correlations and genuine quantum entanglement. These Bell tests involve measuring entangled particles in specific ways and comparing the results against predictions based on classical local realism versus quantum mechanics. Every experiment conducted to date has decisively favored the predictions of quantum mechanics, providing overwhelming evidence for the reality of entanglement. This empirical confirmation has transformed entanglement from a theoretical curiosity into a fundamental resource for quantum information science. The counterintuitive nature of entanglement, far from being a mere academic abstraction, is what gives quantum technologies their extraordinary power. It allows for the creation of quantum bits, or qubits, that can exist in superposition and be entangled with other qubits. Unlike classical bits that can only be 0 or 1, a qubit can be 0, 1, or a superposition of both. When qubits are entangled, their combined state holds exponentially more information than classical bits, forming the basis of quantum computing's parallel processing capabilities. This unique property allows quantum computers to tackle problems that are intractable for even the most powerful classical supercomputers, opening doors to breakthroughs in medicine, materials, science, cryptography, and artificial intelligence. In essence, quantum entanglement is not merely an oddity of the subatomic world. It is a profound and deeply interconnected aspect of reality. It challenges our understanding of space, time, and causality, yet simultaneously offers unprecedented opportunities to harness the very fabric of the universe for technological advancement. As we move from theory to application, entanglement is no longer just spooky action at a distance, but a tangible and powerful resource for the next generation of scientific and technological innovation. The journey into the quantum realm, spearheaded by the understanding and manipulation of entanglement, is only just beginning.